Okay, hello everyone. Today we will learn about the chapter 11, Linear Models and Estimation by Least Square, part 5. Today we will learn chapter 11.7 and 11.13 together. So I will explain 11.7 first, which is predicting a particular value of y with a single linear regression situation, and I will also explain 11.13, which is predicting a particular value of y in multiple regression situation with vector notations. So let's go first for predicting a particular value of y in a single regression situation. So far we learned how to do the inference for a given point x star. In this case, for a given point x star, the expected value of y is something like this, and in this case we can set a0 equals 1 and a1 equal to x star, and put it on our theta, which is linear combination of beta 0 and beta 1, and we derive the variance of y is this one. Let's think about the other case. What if we observe the new observation y? So we wish to predict the particular response y that we will observe if the experiment is run at some time in the future. So what would be the difference? So let's think about more deeply on this situation. So notice that y is random variable, and if we are interested in the value of y when x is x star, call it as y star, we could employ y hat star, which is this one, as a predictor of a particular value of y star. And if our future observation x is x star, then the error of predicting a particular value of y star can be expressed as this way. So y star minus y star hat could be error, and this value is unbiased. We can easily show that expected value of error is expected value of this thing, and which is expected value of y star minus expected value of y star hat. And since this one becomes y star hat is beta 0 hat plus beta 1 hat x star, and so this one it becomes beta 0 plus beta 1 x star, and so this one minus this one equals 0. And what else? And let's move on to calculate variance of error. And again, the variance of error, which is variance of y star minus y star hat, which is variance of y star plus variance of y star hat minus 2 times covariance of y star and y star hat. And one thing that you can notice is that the future value of y star is not employed in the computation of y star hat. So for the computation of y star hat, we used the x1 to xn, which is y1 to yn, which is previous observations, and for the y star, the future observation, which is yn plus 1. So the computation of y hat star, this one is independent of the future observation. So y star and y star hat are independent. So this covariance part goes 0. And so variance of error is variance of y star plus variance of y star hat. And so the variance of y star, the y star is beta 0 plus beta 1 x star plus epsilon, let's say this is epsilon m plus 1, since we can think of this y star can be n plus 1th observation. And so the variation of this one is dependent on here, so this is sigma square, and plus what is variance of y star hat? we already calculated the variance at the point x star, which is sigma square 1 over n plus sxx here x star minus x bar squared. And so the result is this one. So the intuition here is that for the future observation, y n plus 1, you will going to have beta 0 plus beta 1 x n plus 1 plus epsilon n plus 1. So this variation for the future observation, we have this variation is also added for the future event. So the variation from this epsilon n plus 1 added to our variance. That's this part. So you can intuitively understand this situation this way. So in the future event, you will going to have epsilon n plus 1, and so that part can be considered in the calculation of variance. Okay. So as a result, we can derive the distribution of this thing follows the normal distribution, and if we substitute for sigma, we can find also this. And actually, there are some hidden steps from here to here. And in the previously in theorem 7.3, we learned that s square is independent of y bar. And so, actually, for this case, we can derive similar theorem. I will not explain the details, but the sum of square error is independent beta 0 hat and beta 1 hat. We can derive something like this, and also we can derive SSE divided by sigma square follows chi-square distribution with n-2 degrees of freedom. So if we derive this result, and then we can derive this t distribution. Actually, the t distribution is z divided by square root of w divided by nu, which is degrees of freedom, and let our w as n-2 times s square, and here s square is SSE divided by n-2. Okay, so let's define our w as this thing. Then we can find that this w follows chi-square distribution with n-2 degrees of freedom, and if you put n-2 s square here in w, and let's put nu as n-2, then n-2 cancelled, then you can derive that the t distribution of ours is this thing, and degrees of freedom is also n-2. You can derive this thing. Okay. And as a result, you can derive the 1 minus alpha % prediction interval for y when x is equal to x star, which is this thing. And notice that this is the prediction interval. So this is interval for the future observation. So for the prediction interval for the future observation, it have hidden epsilon n plus 1, which is future error, and so we added this variational term and to calculate the confidence interval. Okay, let's move on to example 11.7 so that how we can use this formula. Suppose that the experiment that generated the data of example 11.1, again we are using data from example 11.1 and is to be run again with x equals 2, predict the particular value of y with 1 minus alpha equals 0.9. And at this time, we want to predict the future observation at x equals 2. So we need to use this formula, and so the calculation using R is as follows. The formula for this thing is here. And so the confidence bound can be calculated as something like this. So this Qt is this thing, and square root of s squared, which is this thing, and the other part, square root of this thing, is this part. So check the items one by one, and then you will understand why these terms are related to this calculation. Okay. So let's visualize the result so far. So let's say our observation is something like this. And if we fit the regression line, that's this one. And for the particular point, if we calculate the confidence interval of expected value of y, which is this black line. However, if we are interested in the future value, which is a new value, then the prediction band, so the prediction band is actually larger than the confidence band of expected value of y. So for the given data set, the confidence band is this black line, and if we want to draw the prediction line, like if you want to draw the prediction band, and then it actually this is actually yn plus 1, and which contains epsilon n plus 1. So you are containing more error for the future value. So we are going to have more larger prediction band than the confidence band. Okay, so you should understand this situation. Let's move on to multiple regression case. So the calculation is similar. The derivation for the error is the same. So the error is y star minus y star hat, and where y is defined like this, and y star hat is defined as this thing, and a prime is this thing, and beta hat is beta 0 hat dot 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 beta k hat. Okay, and so you can also easily calculate that expected value of error is 0, and because this thing is beta 0 plus beta 1 x1 star plus beta 2 x2 star plus dot 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 plus beta k x k star, and which is same as this thing, so this is 0. Also, to calculate variance part, you can derive similarly. This thing becomes variance of y star plus variance of y star hat minus 2 times covariance of y star and y star hat. And actually, this part computed from the future value, and this part is calculated from the the previous values, like from y1 to yn, and this is from yn plus 1. So they are independent events. So this covariance part is 0, and the variance of y star, which is actually beta 0 plus beta 1 x star plus epsilon n plus 1, and so the variance of this thing is sigma square, and variance of the previous calculation, the y hat star, this calculated from y1 to yn, and also we know the variance of y star hat, which is this thing. As a result, the variance of error part is sigma square 1 plus a prime x transpose x inverse a. And again, you can interpret this additional term. So intuitively, you can interpret this additional term as for the future event. So when we are predicting for the future event, which is yn plus 1, this one contains epsilon n plus 1. So you need to consider this additional variation in the calculation of the variance of the error. So this plus 1 part added to when you are predicting the future. So when you are predicting the future event, you will going to have variance of this thing, and so related normal distribution would be this one, and if S substituted for sigma, you are going to have T distribution like this. Again, from the derivation from Z to T, we have similar theorem like 7.3, which is SSE, this time SSE divided by sigma square follows chi-square n minus p, and also s square, which is SSE divided by n minus p. This s square is independent to the beta hat. So s square is independent of beta hat, and also SSE divided by sigma square follows chi-square distribution with n minus p degrees of freedom, and to what else? And so if you calculate your t as z divided by square root of w divided by nu w square, and let your w square as this thing. If you let your w square as this thing, then you will going to get this t distribution. And here again, you can think of that this if you use this thing and this thing, you can derive that this result follow t distribution with degrees of freedom is n minus p. Okay. And as a result, a 100 times 1 minus alpha % prediction interval for y when x1 is x1 star, and x2 is x2 star, and xk is xk star, which is the future value, then the confidential bound, the prediction confidential bound can be calculated like this. Again, you should take care of this part. So if you are calculating confidential bound from the current situation, if you are calculating confidential bound of expected value of y, then you don't need this 1 plus term. But if you are calculating prediction interval, then it is containing future event, which is yn plus 1, which include epsilon n plus 1. So you should consider the variation from this epsilon n plus 1, which is this 1 plus term. And okay, and with this formula, let's try to calculate the same example, which is example 11.17. Suppose that the experiment that generated the data of example 11.12 is to be run again with x equals 2. Predict the particular value of y with 1 minus alpha equals 0.9. Okay, so previously, for the same data set, let's calculate with matrix term. So in this case, we can define our x as this way, minus 2, 1, 0, 2, 1, 2, which is our x, and y is this thing, and to calculate s square, we can use the notation y minus x beta transpose y minus x beta divided by n minus p, which is n minus 2. And this is this part, the line 76. And also the variance part, you can calculate it as x transpose x inverse as the variance part, and what else? So to calculate this thing, you can calculate the confidence interval bound like this. So this qt part is this part, and square root of s square is this thing, and this square root of 1 plus a transpose times variance sigma times a is this part. And so as a result, our confidential bound calculated this way, which is same as the previous example from the simple linear regression case. Okay, let's move on to exercise 11.43. Refer to exercise 11.5 and 11.17. Use the data and model given there to construct 95% prediction interval for the median sale price in 1980. And the exercise 11.5 is this thing. What did housing prices look like in the good old days? The median sale prices for new single-family houses are given in the accompanying table for the year 1972 through 1979. Letting y denote the median sales price and x the year using integer 1 to 8. Fit the model y equals beta 0 plus beta 1 x plus epsilon. What can you conclude from the result? Okay, so our x is year, and so y equals beta 0 plus beta 1 x plus epsilon. So this is our model, and here x is year, and this year is coded as 1 to 8, and y is here. And so you can calculate beta 0 hat and beta 1 hat, and also s square, so related things, and also you can construct a 95% prediction interval from the formula from the previous calculation. So let's try to calculate related terms. So our xi, this is from year 1 to year 8, so which is 1 to 8. So this xi is 1, 2, 3, 8, and our y vector is this thing. So here, and we can calculate the SXX, which is sum of xi minus x bar squared, and also SXX, SXY, SXY, and SYY. We can calculate these terms, and the beta 1 hat, this is beta 1 hat, and this is number of number of data sets, which is n, and beta 0 is beta 0 hat. You can calculate beta 0 hat, beta 1 hat this way, and these are calculated values, and we can calculate SSE and S square like this, and from these results you can calculate the prediction interval using the formula. So for the prediction bound, you can use the formula like this, and so from this calculation you can conclude that this confidential bound is 59.73 to 70.57, something like this. Okay. Now let's try to solve this example exercise 11.43 again with matrix notations. So to prove this thing, we can use matrix form, like we can set our X matrix as there's 1 1 1 1 1 and 1 2 3 4 dot 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 8. So this is our X matrix, and our Y matrix is 27.6 dot 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 62 to 9, and this is our Y vector, and we can calculate our beta hat as X transpose X inverse X transpose Y, and what else? And we can construct 95% prediction interval using this formula. And so let's try to solve the same problem with matrix notification. So our X matrix, this thing can be written as this, and our Y vector can be written as this thing, and the n, the number of observation, is length of Y, and the dimension of X, the number to estimate P, which is 2, and X star, we are predicting sales price for 1980, which is coded as 9. So our X star value is set to 9, and our A, the prediction point, is 1, X star. Okay, and our beta hat can be calculated like this, and our S square can be calculated like this, which so this is Y minus X beta hat transpose Y minus X beta hat divided by N minus P, which is S square. This is the X transpose X inverse calculation, and with these numbers we can calculate the confidential interval bound, which is this thing, and here Qt of this thing is this, and square root of S square is here, and this part is this part. Okay, and to calculate the confidential bound, which is Y hat minus confidential bound, and Y hat plus confidential bound, which is this thing. So this result is same as the previous calculation, 59.73 to 70.57. Okay, so this is the confidential bound for predicted value. The homework for 11.7 and 11.13 is this.